Get started. Please give Gerald and Roger a very great DEF CON welcome.
Hello, DEF CON. Hello, everybody. Today we're going to discuss the current state of DNS rebinding, including recent attack and prevention technique. We will also discuss our tool, Singularity of Origin, the DNS rebinding attack framework, and how it incorporates this new technique and how you can use them today. So our contribution in the domain of DNS rebinding are twofold. The new tool, Singularity, it has everything you need to perform DNS rebinding. It is reliable, it is performant, it has built-in payload for command services, and can perform automatic service detection and exploitation. The second area of contribution is in the research of technique to improve the speed of DNS rebinding and how to bypass command DNS rebinding protection. So our talk will be articulated around the new tool and the techniques it incorporates, and we will include a customary refresher on the basic of DNS rebinding. We will also discuss an architecture we have implemented in Singularity, which allows you to interactively browse a hooked browser internal network. So who are we? We are Gerald Dussault and Roger Meyer. We are security consultants at NCC Group. We are attached to the San Francisco office, and we are the authors of Singularity of Origin. Roger.
So why should you care about DNS rebinding? Most developers understand that when they bind their application to all interfaces, that they expose themselves to remote access, and this is not a good idea. So what do they do to fix this? They bind the application to the local host. They think only trusted users can access. It's a trusted environment, so they don't need authentication, right? And then all these DNS rebinding issues happen. The EOS cryptocurrency wallet is vulnerable. Google Home, Roku, Sonos speakers are vulnerable. The Geth Ethereum client was vulnerable. Redis, Memcached, Elasticsearch, the Kubernetes dashboard on Minikube is vulnerable to DNS rebinding, allowing RCE and VM escape. The Rails web console was vulnerable. We see more and more applications exposing a HTTP server on the local host, especially through the popularity of frameworks such as Electron. The rise of IoT devices exposing sensitive interfaces on internal networks without authentication will make this even worse. We would also like to clear up certain misconceptions, such that DNS rebinding is slow and can be solved by out-of-the-box DNS filtering products or services, which is not the case. We would like to start with a quick refresher on how DNS rebinding works. The origin consists of the scheme, host, and port. Two documents share the same origin if they have the identical scheme, host, and port components. The same origin policy is an important security concept implemented in browsers that dictates how two different sites with different origins can interact with each other. Certain interactions are always allowed between all origins, such as form submissions, links, redirects, content embedding, but cross-origin reads are typically not allowed. This is important, for example, if you're logged in to gmail.com and browse to an attacker-controlled website, you don't want the attacker-controlled code to be able to read your Gmail messages. DNS rebinding permits us to bypass this same origin policy. We'd like to show you a visual walkthrough to make it easier to understand the concept. So on the left side, we have the victim, which is the browser. We have a target service, which can be a service on the victim's local host or on the internal network. We have an attacker, which consists of a DNS server and a web server on this public IP. So on the right side, we have the internet. On the left side, we have the intranet. the victim can access the target service without authentication, and the attacker cannot directly reach the target service, otherwise we wouldn't need DNS rebinding. So step 1, the victim browses to the attacker's website hosted on rebinds.it, that's our domain name. We respond with the DNS record of the public IP address and load some JavaScript which keeps running in the victim's browser and waits until the DNS record expires. Once it expired, we make another request with the same origin. This time we respond with a different IP address, the IP address of our target service, 127.0.0.1. Notice that the origin, rebind.it, did not change. We did not violate the same origin policy. The browser will make this request and will allow the JavaScript to read the response and where we can exfiltrate it back to the attacker. All of this is possible because we did not violate the same origin policy. It's still pointing to rebind.it. We only changed the IP address. This was a high-level overview which omitted a lot of details. There are a lot of previous good research which you can look at if you want to know more about the details. We would like to show you a first demo on iOS using Safari where we can achieve DNS rebinding in just 5 seconds using the cache flooding technique. In this case, we will be exploiting a home router on router.asus.com, and we will be just reading the index page and displaying the results in a JavaScript alert box for demo purposes. So this is Safari. We're going to router.asus.com. This is the target we're trying to exploit. So now we're setting up the attack. We're going to the Singularity Manager web interface. We're setting the target host to router.asus.com. We're leaving the target port at port 80. We're setting the attack payload to a simple fetch get. We're using the first then second strategy, an interval of 1 second, and we're enabling the cache flooding technique. We're starting the attack. This only takes about 5 seconds, and we display the results. What we see here is the return of the index page, which is just a redirect to the main login.asp web page, but it shows that we were able to read the response from an internal system, the home router.
Thank you, Roger. Now that we have a grasp on the basics of DNS rebinding, we are going to explore how we made DNS rebinding more reliable within Singularity. So let's say that you are a fan of horse riding and you're trying to plan your next vacation, and you found a website that just allows you to do that. There's nothing wrong with this website. Displayed prominently is a Trojan horse picture. In fact, the website was compromised and is running a hidden iframe with Singularity. So you connect to the website and you download the malicious JavaScript from Singularity, and the code emits its first DNS query. So what is in a query? As you can see, the query is made of several components. These components encode everything Singularity needs to perform an attack. So first you have a start tag. Then you have the attacker host IP address where we run Singularity. Then you have the target IP address, or it can be a name as well, followed by a session ID. Session allows for the use of concurrent users and targets. Then you have the DNS rebinding strategy. Singularity incorporates a number of different DNS rebinding strategy. Here you can see FS, first then second, also known as a time-varying attack. This is the simplest and most reliable DNS rebinding strategy you can implement. Then you have the end tag, and then you have the attacker domain, the one that you have either purchased or compromised. So to improve reliability, you want to remove any HTTP performance enhancing technique that may impede DNS rebinding or stop it completely in its track. So we try to disable HTTP caching in all browsers implementation and intermediate cache to ensure that the browser get a fresh copies of all the resources. We also instruct Singularity to drop idle connection from browsers. So when it is time to rebind against the target IP address, the browser doesn't maintain a connection to Singularity. What about TTL value? Most literature and other tools use a value of 1 second. We tried 0 in the hope that it will break stuff. It didn't. 0 second is a valid TTL value, so we just stick with that. So how do we know that we have successfully rebinded against the target service? Historically, Singularity used an index token in the HTML body. So if this index token is present, then the JavaScript code knows it's still pointing against Singularity. If this token disappears on the next fetch, then it means that you have successfully rebinded. We recently moved to a custom HTTP header. However, the index token is still useful in one specific DNS rebinding strategy where we abruptly terminate the connection from Singularity to the browser, and the browser gets confused. We will go into more details on this later. Something you need to consider as well is that you may encounter an environment where there is an IPS and IDS, and these IPS IDS may emit their own spurious DNS queries when they see requests from the target browser. So it means that you may receive IP address out of sequence when you make your DNS query, which means that the target browser will never see the IP address of Singularity, only the targets, so will never be able to download the code and perform DNS rebinding. So to address that, we have implemented a random DNS rebinding strategy where we respond either with the attacker IP address or the service IP address, which is a much slower technique in general, but you could get lucky. So we're now going to explore how we improve the speed of DNS rebinding in Singularity. So the first thing to know is that implementation details matter. The DNS rebinding speed will vary depending on the host implementation, whether you use a Windows or Unix-like environment or operating system such as Linux or macOS. The browser vendor, i.e. Edge, Firefox, Chrome and all its spin-off, and Safari. The target specification matters, whether you use a service, you're targeting a service that's bound to the loopback interface or on the private network or a remote public IP address. Obviously, we just saw that external factor may impact the speed, such as the presence of an IPS and IDS. So just to illustrate, DNS rebinding may take 40 plus minutes when using Edge and down to 3 seconds depending on what strategy you use. Singularity can automatically fingerprint to optimize for speed in some condition. We will discuss this later. So the time varying attack Singularity first and second is approximately 60 seconds on all browsers except IE and Edge. There's another technique called multiple answers that we didn't believe would work. However, one of our colleagues, Michael Roberts from NCC Group, created a small proof of concept demonstrating that it was working on Windows when you specified an IP address of 127.0.0.1, and we were achieving rebinding time of 3 seconds once we implemented that. However, it didn't work with, the same technique didn't work with a Unix-like machine, such as Linux or macOS. However, after a bit of digging, when we specify a target service IP address of 0.0.0, we achieve approximately 3 second rebinding time. So now we have a solid and fast DNS rebinding against all loopback-bound services. Just to illustrate at a high level how the multiple answer rebinding strategy works, So the target browser will emit its DNS query to rebind.it, where we run Singularity as usual. Instead of responding with the IP address of the attacker, then the IP address of the service, as we do for the time-varying attack, we respond with both records at the same time. So then the target browser is going to keep polling the service and to determine whether it's pointing against Singularity or the target. Singularity is going to then implement at some stage ephemeral firewall rule that will abruptly block the traffic. This will force the browser to connect to the target service using the second IP address we provided earlier. So the multiple answer technique or strategy work very well for loopback bound type of services. So if your service, for instance, is listening on 127.0.0.1, but we were getting inconsistent results for over target specification, for instance, on the private network, where 1 attempt out of 5 would succeed. We implemented another technique called DNS cache flooding. This worked very well in Google Chrome and Safari and iOS platform. You basically flood the cache of the browser with thousands of queries, and you can reduce then the DNS rebinding time from 5 to 40 seconds, which is a great progress over the average of 60 seconds. Roger Demo was using this technique when we were using iOS, and we got a rebinding time of 5 seconds. Flooding the cache is performed in a separate web worker. So here you have a Chrome console, and in blue you have your regular attempt to fetch resources to determine whether we were pointing against the target service or not. And in between all these requests, you have thousands of queries that fill the cache of the browser, the DNS cache, in an attempt to evict the IP address of the Singularity server, forcing then the browser to point to the service, for instance, 127.0.0.1. So we have illustrated in this table some configuration and what can you expect from a DNS rebinding time perspective. Roger?
Let's talk about DNS rebinding protection bypasses. Using Singularity, we can bypass all known DNS rebinding protections, such as those implemented in open source DNS servers Unbound or DNS Mask. We would like to emphasize that common recommendations and default configurations do not provide complete protection. How do common DNS protections look like? Most solutions block certain DNS responses at the perimeter, so when they enter your internal network. Some tools block RFC 1918 private IP addresses such as 10/0, 192.68/0. Some tools block localhost IPs, 127/8. Some tools can be configured with which IP addresses you're using internally. If you're using public IPs on your internal network, you can get those blocked. Some tools block the 0/8 range. DNS Mask and Unbound are two widely used open source DNS servers. They're used in tools such as pfSense, OpenWRT, and certain home routers. There are also free public DNS services, such as Cisco's OpenDNS, which advertise that they have DNS rebinding protection implemented. For OpenDNS, it's called block internal IP addresses, and that just blocks private IPs. DNS Mask has a setting called Stop DNS Rebind, which blocks private IPs, the 0/8 range, and the 127/8 range. This does not block localhost. We will talk about what we mean by localhost in a minute. The Unbound DNS server has a configuration setting called private address, where you can configure the internal IP address range, and this will then be blocked. This does not block the 0000 IP, the 127.0.0.1, or the local host. Our first protection bypass is using the 0.0.0.0 IP address. This is a non-routable or invalid IP address, but it works very well on Linux and macOS using Firefox and Chrome to access the local host. This bypasses protections that block DNS responses containing the IP address of 127.0.0.1 or the whole 127/8 range. When we query Singularity, we can specify the target here, so we can use the 0.0.0 target, and then the DNS response will be an A record pointing to 0.0.0.0. What if the DNS protection solution blocks all internal IP addresses? Then we can use CNAMEs. Canonical name records are DNS records which map one domain name to another domain name. We can return a DNS C record instead of an internal IP address, such as wiki.nccgroup.com or jenkins.internal.cart.com, whatever our target is. This bypasses protections that block DNS responses of private IP addresses. The local internal DNS server will then resolve the CNAME for us, and you don't want to block internal DNS resolution if you want to use internal host names. When we query Singularity, we specify the target here. So instead of an IP address, we specify wiki.nccgroup.com, and then the DNS response will be a CNAME pointing to wiki.nccgroup.com. Our third bypass is a variation of the previous technique. We can use the CNAME of localhost. This bypasses protections that block DNS responses containing 127.0.0.1. This works well in Linux and macOS. When we query Singularity, we specify localhost here, and then in the response, we just return a CNAME pointing to localhost.
Okay, now we're going to discuss the architecture we implemented in Singularity to browse a victim internal network after a DNS rebinding. So tools such as BEEF, the browser exploitation framework, and FireDrill, a DNS attack tool, can use a hooked browser to access targets which are not typically available directly from an attacker, such as your home appliance or corporate environment assets, either via cross-site scripting or DNS rebinding. So we know that BEEF requires the attacker to configure its browser or operating system to use the BEEF application server to avail of this functionality. We don't know how FireDrill does it, since the code and the binaries are not available. We implemented the browsing of service in Singularity without requiring the attacker to setting up its browser to use an HTTP proxy, but instead just to point to Singularity via using normal HTTP requests. So at a high level, once your browser has been hooked, or the victim browser has been hooked, the browser will make a WebSocket connection to the Singularity application server and wait for instruction. The attacker will use his browser to connect to Singularity and display the list of victims that have been hooked and select one to browse. So let's say you want to connect to the home directory of a service bound to 127.0.0.1. The attacker browser will emit a normal HTTP request to obtain this directory. The Singularity application server will translate this into a WebSocket operation to fetch the resource. Then the target browser, using the Singularity JavaScript code, will translate this WebSocket fetch operation into a normal fetch API call to the home directory. Then the data will be sent back all the way back to the attacker browser. Sorry. At a low level, we just customize the Golang round-tripper interface, and we use the WebSocket plaintext protocol to package each fetch request and response. Since we use base64 encoding, the size of the message is increased by 4/3 of the original length of the message. Please note that you don't have to use a browser. You can use any user agent. You can use curl, HTTP inspecting proxies such as burp port swigger or wasp zap or SQL map and so on. So when we implemented this architecture in Singularity, we encountered a number of challenges. The first assumption we made was that we didn't have to care about the cookies exchanged between the victim browser and the victim service, the target service. However, our first test case was Duplicity, a backup solution that was vulnerable to DNS rebinding. And as you can see, the code snippet here, Duplicity is extracting CSRF token from the cookie to generate links that allow you to browse the Duplicity application and perform a number of actions, including running a backup. So Singularity didn't work with that. So we had to consume this cookie. So we read them from the target browser, and we transmit them to the Singularity server over WebSocket, and then the Singularity application server set them on the attacker browser for the target domain that Singularity has constructed. For HTTP-only cookie, we don't really care about them. They cannot be read by JavaScript, so they cannot be used by JavaScript on the attacker browser. So we let the target browser handle them for us. Another challenge is that to be able to read a cookie when you perform a fetch request, a fetch API, you have to pass the credentials include option to the fetch request. And if your application requires HTTP authentication, this is not going to work. And why is that? This is illustrated in this slide. So let's say you have a service that requires HTTP authentication, and you issue the command fetch HTTP 127.0.0.1 with the credentials includes, then an authentication dialog box appears. That will warn the user that something is amiss. So we don't want that. However, if you type the same command but you pass a different argument, credentials omits, then there's no authentication dialog box, so the victim is none the wiser. So when we have cookie and HTTP authentication required, then we forget about, we actually don't transmit the cookie to the attacker.
Okay, now that Gerald introduced us to this hook and control feature, we would like to show you how this works in a demo. For this demo, we'll have two browsers. One is the victim, the other one is the attacker. In this case, they will be both on the same machine, but in a real-world attack, this does not have to be. The attacker can be anywhere. So the victim will have a Jenkins instance installed on the local host, and the attacker will try to access this. So this is the victim Chromium browser, which has this Jenkins instance listening on the local host. Now we're switching to the attacker. This is the hooked victim clients, which will show up here. So we reload the page and show it's currently empty. There's nothing there. Switching back to the attacker, to the victim browser, we're going to the Singularity Manager interface. We're setting the target to 000 for localhost. Target port is 8080. We're using the hook and control attack payload. We're using the multiple answers attack strategy. We're using 1 second interval. We're starting the attack. It only takes 3 seconds. The attack was successful. We're switching back to the attacker. We're reloading the page, and we can see this new victim session. So we click on it, and we can now browse the victim's Jenkins instance over the internet. So the attacker browsed this credentials endpoint. We're going back to the victim to show you the requests. The first request is this /credentials, which the attacker was browsing to show you how this looks like. We can see /credentials. The remote address is 000 for localhost, and the request URL is the origin, still points to the attacker. We'd like to show you how we exfiltrate our data back to the attacker. So this SOOWS endpoint is how we send and exfiltrate the data back to Singularity using WebSocket messages, and that's how the attacker can then browse to the Jenkins instance.
Okay, now we're going to discuss how to scan for vulnerable hosts and services. So in the past, there have been many very smart attempts to replicate Nmap behavior in the context of the browser, but without the power of raw sockets. So many of the solutions we have looked at are either not completely reliable or do too much for our purpose. For instance, we don't care whether SSH port is open or not. DNS Rebinding is concerned with exploiting issue with HTTP resources so far. So the only thing we care about is does it speak HTTP. So we implemented a very simple solution that leverage modern API, and so it's including fetch abort for implementing a timeout. So we distribute the list of targets we want to scan that includes IP address and ports across 4 web workers. We only fetch the resource header. We don't bother with the response body. And we have a hard-coded limit of 300 milliseconds before we move on to the next target if we don't get sufficient results. So the timeout will obviously drive how fast you can scan a host or a whole network. It is fast for HTTP open port, obviously, and it's fast as well for closed ports, because if you send a packet to a closed port, the TCP/IP stack of the target will respond with a reset packet if nothing is listening on this port. It is slower for firewall ports, but because here typically a firewall will drop any response, so you don't know what's going on. So the scan will wait 300 milliseconds and then move on to another target. And slow as well, possibly for slow HTTP service and other protocols that are not handled by fetch. So you want to use a lower timeouts when you're scanning a LAN or fast HTTP service, or you can use higher timeouts when you scan over a network, including one that I have high latency, such as a VPN. Other interesting bits and pieces, we use the classic WebRTC IP address leak to obtain the IP address, the private IP address of the victim. When available, it works on Chrome and Firefox. And we use this IP address to derive a subnet we can use to scan. We obviously pass the credentials omits to fetch, so the victim is not made aware that a scan is ongoing, and we're currently considering performing a second pass scan to identify slower HTTP service that we may have missed. So we have learned how we made Singularity more reliable, faster, how we can find vulnerable targets and services. Now we're going to show you how you can implement all the above, orchestrate all the above, and perform service detection and auto-exploitation as a bonus. So Singularity provides a sample autoattack.html file, automation file. It is fully customizable and permits to leverage all the features we have discussed so far, including but not limited to, you can specify a specific exploitation payload, for instance, targeting a service like Jenkins, or you can ask Singularity to auto-select the payload based on the service it detected. You can hard-code your targets and add Singularity to optionally detect more targets, maybe on your network. Same thing for ports. You can specify a default DNS rebinding strategy and ask Singularity optionally to auto-optimize and find the best strategy for you. And obviously, you have all your options, such as flooding the DNS cache, visibly hiding activity, and so on. In the future, we intend to implement more auto-optimization, so you don't have to read the extensive wiki. So when you're designing your attack, you want to mix and match different specification of the same targets. For instance, for local host bound service, specify 0.0.0.0, localhost as a CNAME, or 127.0.0.1. This will improve reliability, permit you to bypass security controls, and for speed. You can instruct Singularity to find and use the external IP address to exploit the internal interface of Wi-Fi access points and routers for a device that use the weak AND system model. I can only encourage you to refer back to the DEF CON presentation, DEF CON 18, in that regard to see how it works. And you want to do some homework using open source intelligence. Try to figure what is the naming convention for assets in a corporate network, or even use a dictionary of service name and specify them as CNAME in your targets list. For instance, jenkins.internal.corp.com. This is likely going to pay off because a lot of services are still unauthenticated in a corporate environment. So we mentioned that Singularity can do service detection as well. So Singularity comes with a number of attack payloads that target services such as Ruby on Rails, the admin console, Amazon, AWS instance metadata, and so on. And we recently added a service detection routine that allows you to detect what service is running behind and try to deliver an appropriate payload. So for instance, if you find that the service responds with a HTTP header that contains the value X Jenkins, then Singularity will figure out that more than likely is facing a Jenkins application instance. So when you select the automatic attack payloads, Singularity will try to detect the service and deliver the appropriate payload it has. So with our tool, we were trying to blur the line between origin, and I think we have achieved that, hence the name, Singularity of Origin. So how do you protect from DNS rebinding attack? You often hear comments or on blogs or recommendation to use DNS blacklists, or to use, tentatively to use DNSSEC maybe, or to use this DNS service provider, or one of your colleague or friend bought this appliance that, or router that states that it provides DNS rebinding protection. Well, as we learned, command wisdom is not enough. It is hard to understand all the subtleties of DNS rebinding, and no DNSSEC won't help you there. So Roger, how do we protect from DNS rebinding?
There are 3 proper ways to protect your service. One is to use TLS on your application, including the service listening on localhost. You can require authentication. If the attacker doesn't know the credentials, they can't make a valid request. Or you could validate the host header for all incoming requests using a whitelist of trusted domain names such as localhost or 127.0.0.1. Remember when we showed the origin in our last demo, it was still pointing to the attacker, which won't be whitelisted. There is also a proposal called Course RFC 1918, which would require a pre-flight course request for websites hosted on a public IP address when they make a request to a private IP address. This is currently a draft and not shipped in any browser, but this may prevent DNS rebinding in the browser. We have one last demo where we show you how to automate this whole process. So previously, the victim was browsing to the Singularity manager interface where they had to configure everything, which is not very realistic. So in this demo, we'll show that the victim only has to browse to Singularity. We start with a port scan to detect services listening on the local host. We rebind to these discovered services in 3 seconds, already detect the service listening for the payloads we have, and launch the exploit right away. For this demo, we have a Rails console listening on the local host, port 3000, and a Jenkins instance listening on port 8080. So this shows the managed web interface, which we are not going to use. What we're going to use is this auto attack demo page. So browsing to the page, we see that we detected port 8080 and 3000. We're launching DNS Rebinding right away. The rebinding was successful. It already detects the services. It's not showing. Let's go back one more time. It didn't update quite well. It detected Jenkins right away, and it should detect. All right, let's launch. It detected Jenkins, and here it's still rebinding, auto-detecting, but it doesn't seem to update quite well. So for Rails, we have remote code execution, which launches the calculator, and for Jenkins, we just dump the plain text password stored in credentials to the console. We'd like to show you how the script looks like, the configuration script. It's very simple, the auto attack script, so we can define the rebinding strategy. Here we use multiple answers. We use the attack payload automatic, which automatically tries to detect the service. We specify the ports, port 8080 and 3000 in this case only, and we can specify which address to use. There are a few more settings, but which we don't need for the. You can get the slides, including our notes, on this URL. You can get Singularity, our tool, on our GitHub page with all these features. And let us know if you have any questions. Thank you.